Okay, so now we're going to derive the Crank-Nicolson method. So before we had this expression right here, and that's basically what we approximated our equation to be for our in equation 2 for our calculating our temperature profile. But now, as we've seen, we have the constraints of R being less than 1/2. So when we use the Crank-Nicolson method, we actually don't have these constraints. And we're going to show that, and we're going to first derive the Crank-Nicolson method, which is a little bit more complicated, but it makes a little bit more sense to use this instead of the other method. So basically, this part right here is going to be the same. So we're going to end up having, we're going to have a tjn plus 1 minus tj to the n, and then we're going to have delta t. So this part's the same as the other one, as our what we derived in equation 2 before. So we have our j right here, j right there, and then that will equal our alpha over our delta x squared. And then, so basically what we're going to want to do, what's different from the Crank-Nicolson method is that it approximates, in this case we just approximated our second derivative from the earlier time step and the previous time step, or the later time step. Now we're going to approximate the second derivative by doing the average of the earlier time step and the later time step and the previous time step. So that's going to look like this. So we're going to have n j plus 1 to the n plus 1, and then that's going to be minus 2, and then j at the later time step, and then plus t at j plus 1 at the later profile at the later time step, and then that is going to be one of our expressions, and then for the second derivative, and then we're going to take the second derivative from the other time step, which is the original time step. We're going to have tj plus 1 to the n, previous time step, minus 2 tj to the n plus tj minus 1 to the n. And then since we're going to be taking the average of both of these, the average of our second derivatives, that approximated second derivatives, we're going to basically divide this by 2. And that will give us the average. And now we can combine a little bit of terms. So basically what we're going to want to do is we can say this tjn plus 1 equals tj to the n, and then we'll have plus, since we're adding this on that side, we'll have plus our alpha over delta x squared, and then this will be times 2 since we multiply the 2 out of there. And then this will be, we'll put our expressions in there. So we have tj, we're just copying from above, tj plus 1 at the later time step, n plus 1, minus 2 tj n plus 1 plus tj minus 1. And this should be a minus 1. And then so we have our tj minus 1 at the later time step, n plus 1. And then, we actually don't need parentheses there. And then we'll have our tj plus 1 at n, and then minus 2 tj, a little bit messy, 2 tj at n, and then plus tj minus 1 at n. And basically, and this is our Crank-Nicolson method. It's a little bit different because you can see we have this divided by 2 and multiply out. So this expression right here, this will be our R in this value. So this is our Crank-Nicolson method, the equation that we want. And in this case, we're taking the average of the second derivative approximations from our heat diffusion equation. So this is our Crank-Nicolson method, and now we're going to do a stability analysis. Okay, so to do the stability analysis, we can move our n plus 1 terms onto one side, and then we're going to move our n terms, these ones, onto the other side. So what we're first going to do is move our n plus 1 terms to the one side. So we're going to have negative r tj plus 1 at n plus 1, and then we're going to have plus, and then we'll have And then this is our r right here. This one is our r right here, which I already showed. And then, so that it means we're going to have a 1 plus 2r here. And then that will give us tj n plus 1. And then we'll have an r tj minus 1 from this term. And then at n plus 1. And then that will equal, we're going to put these on the right side of the equation. These will be on the left side of the equation. So then that will equal, we're going to have do the same thing on that side. So we'll have a r t j plus 1 to the n, and then that will be plus, and then we'll have 1 minus 2r here, and then tj at n, our previous time step, and then we'll have plus r at t, the previous position at this previous time step, tj minus 1 to the n. Okay, so now we can do our stability analysis on this. So basically what we want to do next is we can kind of substitute in, when we go back up, we can substitute these in, like when we did the von Neumann stability analysis with the other one, we can substitute these in up there as well. So to do that, we're just going to come back down here, and we can see that from looking at the terms, we just we'll have a tj n plus 1. We're going to factor that out, and then we're going to have negative r, and then if we look at it, it's the only thing different is just that e to the I k delta x, and then we have plus 1 plus 2r from right here, and then we're going to have minus re to the negative I k delta x, and that will be our left side of the equation. And then for our right side of the equation, what we're going to do, I'm going to zoom this out a little bit to give us a little bit more room. So for the right side of the equation, we're going to do the same thing. We just substitute in that e to the ikx. So then we're going to have a tj, and then we're going to have an re to the ik delta x, and then plus 1 minus 2r. And then we're going to have plus re to the negative ik delta x, so just like we did on the left-hand side of the equation. Okay, so where can we go now? So now we can actually substitute in our, when we go back up here, we can substitute in this 2 cos right here. We can substitute in this 2 cos k delta x equation into our e to the ik delta x terms. So we're going to do that next in order to get towards our stability analysis. So what we're going to have is we're going to have a, on this left hand side, we're going to have our tj n plus 1, and that is going to equal our tj at n, our previous time step, and then we're going to have this expression in the numerator over here, and then we're going to have this one in the denominator over here. So we'll have a 2r cos, and then we'll have a k delta x, and then that's going to be 1 or plus 1 minus 2r from over here, because that one's going to be in the numerator. And then in our denominator, we're going to have this left-hand side of the expression, so we're going to divide it over. So we're going to have 1 plus 2r, and then we're going to have minus a 2r cos k delta x. Okay, so we can see, of any values of r, if we want to do our stability analysis, can any values of r make this whole expression less than 1? Well, let's find out. So if we keep going on our stability expression, we can say our tj at the further time step is equal to tj at n, and then times, we have our 1, or factor out there 1 minus 2r, 1 plus 2r, 1 minus 2r, and then that will give us 1 minus cos of k delta x. I believe my math is right there. So if 1 minus 2r, we factor that out, and then that'll give us, okay, yes, okay, that looks right. And then that will give, and then we'll factor on the bottom, 1 plus 2r, and then that will give us 1 minus cos k delta x. And you can see that for any values right here, we can see this a little bit better since we factored out those 1 minus and 1 plus 2r's. We can see that any value we put into there is always going to be greater than 0. It's always going to be positive, always. No matter what, it's going to be a positive number, whatever value we decide to put in there. So now we can see from this is we can say that our tj at n plus 1 is equal to our tj at n. And then this will be times our 1 minus 2r. And then we'll have our, we're going to call these values right here, we're just going to call them y's, which are words are going to say y is a positive integer. Since these will always, whatever expressions we put into those are going to be positive. So we're going to say y is a positive integer. So we can just substitute y in there. So we have 1 minus 2r over y, and then 1 plus 2r put in y. And that will give us a value where r will also be greater than 0 all the time. And we can say this r times y, we can just call that a z. Or we can just say like this value right here, we can just go ahead and call that z, just to make our terms a little bit. So we're just going to say this expression right here, 1 minus z, and then 1 plus z. For all values of z, it's always going to be greater than 0. So from this, we can say that stability constraints in the Crank-Nicolson method basically do not exist. Although when our values of delta x and delta t increase, when those get really large, we're going to end up with some inaccuracies in our differential equation. But if we keep our delta x and our delta t small, basically this Crank-Nicolson method is going to work out really well, and it's going to be accurate because no matter whatever arbitrary values of r that we use, it's always going to be stable. We're not going to have that weird graph. So this Crank-Nicolson works really well for making our graph stable in this case. Okay, so now what we're going to want to do is code out this Crank-Nicolson method from kind of like what we did before, except in this case, we can see that we have this matrix over here for the finite differencing, and we can see that our left-hand side of the equation is in this 4x4 matrix. And from this matrix for our temperature profile, in which the bar is shown right here, we can see that the diagonals the corners are 0, and that just leaves the diagonals that we need to solve. And then for our right-hand side of the equation, we're going to have another variable in which we have this right-hand side vector, and then we're going to iterate through our temperatures to calculate our temperature profile. And also, I should mention, we have this T0 or T0, in which we're going to specify that temperature. It's going to stay there, and then that's going to be the one side of our bar. And this other side, we're going to have this R times T5, which will be the end side of our temperature bar. In order to do this, solve this simultaneous equations for our matrix, we're going to use something called solve-banded. So to do that, we're going to have our from SciPy dot linear algebra, so linalg, we're going to import a function called solve-banded, and basically this solve-banded, it basically solves the diagonals of our 4x4 matrix in this case. Well, in this case it'll actually be a 3x48 matrix, but this is just showing like the concept of what our solve-banded is going to do. Okay, so we're going to go down here. So we just did this in the last coding video. So now we can specify again what our alpha and nx and nt are, which will be the same as up here. So we can go ahead and copy and paste this down because it'll be the exact same. So we're going to copy and paste that down, and that should be good. We're going to just shift enter to make sure. Okay, and we can say that this is all the same, except remember with the Crank-Nicolson method, remember that this was our R value changed when we recalculated our R value. So we need to make sure that this is divided by 2 with our Crank-Nicolson method. And basically what we're going to want to do next is we need to we can specify our initial temperatures. Okay, so to do that, we just need to first set our first temperature, and we need to set the size of it. So we're going to do an np.full, and then this will be the shape, which will be our temperature bar nx, and then we know that it's going to go to what our fill value is. So we can just say 20 degrees Celsius for our first one, and then we'll enter that down. And then we need to specify what our first temperature is. So we'll say that our basically our initial left side temperature of our bar, so this will be the index of 0. We're going to say that that's equal to 50 Celsius. And then we can say, oh, not big length, it always does that. And then we can say that our right side temperature, which will be the end of our matrix from Python using Python indexing, we can say that that will be equal to -1, which will be the very end of our matrix. And then we are going to say this temperature, we can say that this is equal to 80 Celsius, and it's going to stay there. So that will be our right side temperature. So shift enter that. Okay, so now looking at this matrix we have set up over here, that basically shows the stability of why the Crank-Nicolson method works. We have this right side, or we have this left side, and this is where we're going to end up calculating our diagonals. And we can just call this left side, for solve banded, we can just call this left side, we can call this, just go ahead and call this A. So we're going to set the first values, we're going to set them to 0, so we're going to do np.zeros. And then we have, for our matrix, we need to think about it. So we need a row for our lower diagonal, we need the row for the upper diagonal, and we need the row for the middle diagonal, as we can see in this picture over here from our notes. But first we need to basically specify what our A matrix is going to be. So we know we need 3 rows, so we're going to have 3, and then we know that it's going to be it's going to be 3 by what? So we have a bar of 50, but 2 of the temperature are already specified, so it's going to be by 48. So since 2 of the temperatures are already specified, we're going to go nx minus 2. Okay, and then that should basically set up our matrix of our diagonals that we were looking for, because we're going to have a 3 by 48 matrix. So we'll shift enter that, and we can kind of see, shift enter again, and we can kind of see this will be our array. So that kind of just sets all of them to zeros, just to show that. Okay, and next what we want to do is specify what is our upper diagonal. So we're going to have A for the upper diagonal. It's going to start from the very first index, which is going to be 0. And then it's going to go to the second index, 1, and then all the way to the end. So we're going to go colon. And then we know that this, from our matrix over here, this upper diagonal is going to be equal to -r. So we can say that that is equal to -r. And then for our second one, and actually need this into an array, so we need to make sure that that stays in that. We don't need two equal signs, that would mess up our code. So next what we need is to specify our main diagonal, our middle one, which is our 1 plus 2r. So we know that our main diagonal in this case is going to be 1, the first value, or technically the second value. Python indexing starts from 0 all the way to the end. And this will be equal to 1 plus 2 times r. Okay, so we can say that will be our middle diagonal. And then for our lower diagonal, it will be basically the same as our upper diagonal in terms of the -r, except we're going to need to make it the second value, so our third row in this case, but Python indexing starts from 0, so it needs to be 2. And then that will go all the way to the end minus 1 of them. So we need to do -1. And we say that that will be equal to our -r as well. So that will be our lower diagonal. So we'll go ahead and shift enter. And we can just check our A now. Okay, so we can see we have separated our rows into 3 different diagonals right here. just kind of showing what our vector looks, or A matrix looks like. Okay, so now that we have the A matrix, which is our left-hand side of the equation, we need to get the B matrix, which will be our right-hand side of the equation. And basically, this solved bandit is going to be able to calculate the temperature profile through our diagonals. So what we need to do next is specify our B diagonal, and we can just set these equal to 0. So we'll do B equals, and then we'll go NP dot zeros, and then we'll say that this needs to be the shape of this needs to be basically 2 minus the number our temperature bars, since we have the 2 specified temperatures. So that'll be nx minus 2. And then that's going to put in our vector of our right hand side of the equation. Okay, and then now what we need to do is basically set up our vector. And how we're going to do that is we can kind of see on this right hand side of the equation, we're going to have r times this temperature, and then plus 1 minus 2r times the other temperature, the previous temperature at the time increment, and then plus rr at the temperature earlier, or plus rr times the temperature at the earlier time increment. So, and then we're going to have this plus T0, r times T0, and that is going to actually be, that's one of our specified temperature values, so we're going to add that in later, and same with this r times T5. So what we need to do next is we're going to have put in our B vector, and we're going to say, we can say our B is equal to, so we have our r times our second temperature, so we have our r times our second temperature, T, and then that will be to the, that'll be the second temperature, and then to the end, and then we can say this is plus, if we look at our vector, go ahead and look at it, we can say that plus 1 minus 2r, so we're going to have 1 minus 2, and make sure we have a dot there, and then times r, and then we also want to make sure we have that there, so it makes it an integer and doesn't convert it. And then we'll have 1 times 2r, and then we'll have times our temperature from 1 to negative 1. So I have 1 colon, and then we have to the negative 1. And then we'll have plus our r times, if we look over at our matrix, times the temperature at the back of the matrix. So we're going to have T, and then we're going to have our from the all the way to the front minus the second colon, and then minus the temperature that's coming from the back. So we have the -2 minus 2, the temperatures there. So then we'll go ahead and shift enter that, and we can just kind of check our B values real quick. Okay, so that's our array for our B's. We can kind of see how that might be set up already. Okay, and then now what we want to do is specify our r times T0 temperature, as well, or not temperature, vector, as well as the r T5 one in our right hand side vector. So what we're going to do next is put B, and this will be our first, on the left hand side of our first component of our B vector. So it'll be B0, and then that's going to be equal to the first index of our B vector, and then plus r times our initial temperature. So that will be T, and that will be our initial temperature will be T indexing of 0. And then same thing for the last temperature, except we just do it with the other indexing. So we just do -1 because it's the last temperature, and that is going to be equal to B times -1, which is the last index, and then plus r times the temperature at the last index, which will be our T5, and shown in this picture, but it technically won't be our T5, it'll be more than that. And that will be the last component of the B vector. So we can go off and check our B vectors. Okay, so we can see here that we have a 40 in the front, and we see how these first and last two changed. And we can also check our A to see, and we have these all separated into the in our A matrix. So now what we're going to want to do is use the solve banded function and iterate through this in order to get our final temperature for our graphs, in which will be stable in this case. So now that we have our vector set up as well as our right hand vector set up as well as our matrix from our left hand side of the equation, which is 3 by 48. I got rid of the one notes because we don't need to reference those anymore. So we can make it a little bit bigger. So now what we can go off and do is plot this and then check for the stability. So we'll shift into this. And to start the plot, we're going to go fig, and we're going to say fig 2 this time because we already used fig 1 up top when we tested for the instability plot earlier. So we're going to do fig 2 is make subplots, and then it's going to have rows equal 1 as well as columns equal 1. And then we're going to have our fig 2, we're going to make it a scatter plot. So we're going to do fig 2 add underscore scatter. And then our x will be equal to our x values. And then our y will be equal to our temperature values, T. And then in this case, we can say we're going to call this, we can say this can be through our initial temperature profile. So we can just say that this will be initial. And then this will be our initial temperature profile graph. So this is what our initial temperature profile graph will look like. So we can see we started at 50, and then it diffuses down, and then it goes down, and then it ends at 80. So that kind of just shows us our initial temperature profile graph. And what we want to do now is basically we can go ahead and iterate through this through our solve banded function and solve for a temperature profile across our whole bar with stability this time. So to do that, we'll do the same thing kind of for I in range. So we'll do for I in range, and this will be our time increments plus 1 because Python indexing, and then colon. So this is going to basically iterate through our solve banded, and then basically what we want to do is we can do our solve banded right off the get-go and do 1 1, and then we'll have our A, matrix and our B. And we can try to solve it this way, but when it happens this way, if we go off and look at it, so we can have solve banded 1 from the temperatures, and then we have our A and our B. So we can say we can do it this way, and it shows we have some values here, but it doesn't iterate through our temperatures correctly, and it doesn't basically recalculate our temperatures, which we already calculated up here in our B vector. So what we need to do that is we can iterate through our temperatures in which we're interested in. So we know we need for our solve banded temperatures, we know we have the temperature that doesn't include the first one. So we have our first one, which is technically our second one. This is a Python index that starts from 0, but we already specified our first temperature, and it's going to stay that way. So, and then we're going to have our second to last temperature, so 1 and to -1. And this can be equal to solve banded. Okay, and then next we want to make sure that we recalculate our temperatures that we calculated for the initial temperature profile up here. We need to make sure we recalculate those and iterate them through. So we basically need to update our B values from our matrix before we calculate the next temperature in our on our temperature bar. So what we can do now is we can kind of just go ahead and copy and paste these down through. So we'll have that, and then we can paste these down in, make sure we're indented correctly, and then we'll shift into that. And then now what we want to do is what we did earlier. We want to make sure that we're not plotting, since we have 2,000 time increments here. We want to make sure that we plot only. We don't want to plot all that much. It'll get too crazy. So basically use the module function to only plot our multiples of 10. So we'll do that again. So we're going to say if I modulo 100 is equal to 0, like we did before. So this will only plot every 100 time step. It's not 2,000. And then we'll say our fig2 and dot add underscore scatter. We'll say our x is equal to x. Our y is equal to our T, temperature. And then we can name this something, name equals, and then we can just do the f string again, and we can say, we can make it our iterated values, and if we want to add seconds though, we can have our delta t, and then we can just, this kind of makes it fancy, and then we have our s like that, so it displays it as seconds. for our delta t. So this will show our seconds, and then we show our figure 2. Looks like I need a apostrophe right there, so Shift Enter. And now we can just show our figure. So let's see what it looks like. And we have a mistake here. What did I do wrong? Fig 2 add scatter x equals x, y equals t, name equals f. Let's try running all. Could be the issue. Okay, it looks like it's starting to work, but we're still having a slight issue somewhere. Rows 1, calls 1. Name initial f fig 2 add scatter for I in range of our time step plus 1. Solve banded. Then we have our b equals rt. Then we have 1 plus 2. Make sure that we have all of our integers in here so they don't convert. Let's try again. Okay, it's still not working. I assume that we need to make sure our integers are all set, but I'm still slightly confused what we've done wrong. Are these maybe not tabbed over enough? Unexpected indent, okay, yes, we need to make sure that's over. And then check our figure. Obviously doing something wrong here. Try running all again. Okay, it looks like it's trying to converge correctly, but it's still, I think I'm missing a decimal place somewhere. Because we had this issue in class as well. NP zeros and x minus 2. Name f string seconds r. Thought it was working. Okay, maybe we aren't supposed to specify t right there. So let me go ahead and get rid of that. Run all. Okay, there's still something that is wrong with this. I'm gonna do a quick cut so I'm not just sitting here for a while. Okay, so we have this issue where this is not convergent. So I'm trying to look for my mistake. I feel like this is, I have to be missing an integer somewhere. This should be 2.0. No, I think, let's check our solve banded. Let's check what our solve banded is right now. Okay, that just doesn't look right. Okay, that means we have an issue up here, I think, with something in our vector. NP zeros. We have this all right. Integer right there. Integer. Oh, okay. I think this has to have a colon right here because it's supposed to be going from the second row, and back to our last value. So that could fix our error. Let's check our figure. Boom. Okay, sweet. So it looks like that was our issue there. So we have our figure here. So this shows our temperature profile, and this is the number of seconds it is for each temperature, and our blue one being the initial temperature. And this basically shows our temperature profile. But one last thing we need to do is make sure it's stable. So to do that, we can go back up here, and to change our R values, so we know our alpha, and this is our R relationship in Crank-Nicolson. So we can go ahead and maybe change this bar by 100. So if we change our bar by 100, and if we go off and change our delta X value, if we go off and change that by half its value, put that at 0.5, and then shift enter everything, and boom, we're still stable. And earlier that would have made our thing a lot more unstable. So this shows that our Crank-Nicolson method is successful, and that we are able to make using this method and solving using solve banded through our matrix as well as our right hand side vector. And this basically allows us to say that the Crank-Nicolson method with low values of delta t and delta t still have good accuracy and stability. So let's just make sure it works one more time, and it keeps its stability, and yes, it does. So that will be the end of our exam 3. I've enjoyed making these series of videos. I've learned a lot this class, and I just want to thank Dr. Carlos Coe for a great year.